Welcome to today's Autonomy Talks. Today's speaker is Nicolò Pagan, who is a PhD candidate at the Automatic Control Lab here at ETH Zürich. Nicolò obtained his bachelor in mathematical engineering from Polytechnic of Torino. He then obtained a master in computational science at EPFL. He then worked as a software engineer in the computational fluid dynamics field, which is interesting, I didn't know. And then he joined Professor Dörfler's lab. And today he's going to talk about game theoretical inference of human behavior in social networks. And I'm really looking forward to hearing your talk. So the stage is yours.
Thank you. Thank you, Joelle. Let me share the presentation. Yeah. Can you give me a feedback? Is all fine?
Yes, we can see.
Okay. Okay, very good. Just okay, right. So thanks everyone for attending the talk. And thanks Joelle for the introduction. As you already mentioned, my name is Nicolò Pagan. I'm a PhD candidate at the Automatic Control Lab here at ETH, and yeah, I work this work in game theoretical inference of human behavior in social networks is a joint work with my PhD advisor, Professor Dörfler. So, So let me start with brief motivation. So the main research question that guided my research is, how do social networks form? So here we see an example of agents that may adopt different kind of technology. For example, some of them may use an Apple phone and some others Android phone. And one could argue that the fact that they use the same technology helps us to, for example, establish a relationship. So that means the individual behavior in form of technology that they adopt may determine the structure of the social network. But one could also think the other way around. Like, if there is a new agent that comes in and sees a certain network which is already in place, then he might be more likely to adopt, in this case, a MEC technology, just because the majority of the other agents are using the same technology. And since he wants to be connected with the majority of them, then he may change his individual behavior in order to, say, be connected with most agents. So this very simple example shows that there is a mutual relationship between the individual behavior and the social network structure. So each one influences the other. And regarding social networks, I would like to give a few observations. The first one is that the actors, they decide with whom they want to interact. So for instance, if you're of course familiar with Twitter, then you have a follow button. But so in this sense, you can decide who you want to follow. So the set of your followees. But you cannot decide from whom you are followed. So the directionality really matters. The second one is that when we talk about the social network, then the social ties can have different weights. And well, this sometimes is not so clear. For example, if you consider an online social network like Facebook, where everyone is friend or can be a friend or not be friend with someone else. But of course, all of us, we know that friendship have different weights. The third one is that only limited information is available on online and offline social networks. Of course, we don't know everyone in the world. And at the same time, we don't know the whole LinkedIn network, but what we are usually allowed to explore is the network up to a certain degree of separation from us. So for example, on LinkedIn allows to explore up to the third degree of separation. And the fourth one is that, and last one is that the position in social networks can provide benefits to the actors. And of course, for example, this the LinkedIn example was meant for that, because it was supposed to be a social network that facilitates a change in the career of the actors. And I would like to be more precise on what I mean by benefits that arise from the social network positions. So the first one that we may think about is the social influence. The more people we are connected to, the more we can influence them. So I think this is quite natural, and especially on today's online social network, we sometimes may care about our number of of followers, of people that are following our ideas. But beyond that, especially if we talk with people from sociology, then there are different other benefits that may arise from the social network positions. One of them is the so-called social support. The more our friends are our friends, the safer we feel. And this is the reason why, for example, we like situations where we go out with friends, for example, for dinner, and we like the situation when every of our friends is friends with each other. Conversely, especially when talking about a more competitive context in social networks, the brokerage can be relevant. By brokerage, I mean that the more we are on the path between people, the more we can control. So, for example, we can control, as the guy here in the middle of the network, can control the flow of information between the left part of the social network and the right part of the social network. So this may give a very powerful position to this guy that can control this information. And for those that are familiar with network theory, it's probably quite easy to make an association between these ideas that mostly come from sociology or economics or psychology, and the elements of network theory. So for example, the social influence can be associated with a measure of degree centrality, and the social support with the measure of clustering, and the brokerage with the between centrality of the agents. So the social network formation problem has been considered by a number of communities. As just presented to you, there have been a number of ideas, for example, from sociology or economics. But more than that, even the complex networks community, which mainly is composed by physicists, is considering the same type of problem, together with also people interested in mathematics or engineering or computer science. And to this problem, there have been proposed a number of solutions. For example, the complex networks community proposed the random network models. Among the most famous ones, we have the preferential attachment model or the small world network model, and more generally, the agent-based models. In sociology, the two main streams are called the stochastic actor-oriented models and exponential random graph models. Whereas in economics, the main stream of literature is called strategic network formation models. So this is a highly multidisciplinary field where a lot of communities try to, say, a joint effort in order to reach a solution. And in our work, we will start from the strategic network formation literature, but we will also make sure that we'll consider ideas coming from complex networks as well as sociology. So this brings me to the presentation of our own social network formation model. We consider a directed weighted network G, calligraphic G, with capital N agents in a very general setting. And we consider the weight Aij being a scalar between 0 and 1, which quantifies the importance of the friendship among I and j from I's point of view. What I mean by this is that Aij quantifies how much I is following j, or how much j is important to I. And then we assume that, if you remember our observations, then we assume that a typical action of the agent I is composed by the set of outgoing ties of this agent I. So in this AI vector, I include AI1 up to AIN, which are all the connections from agent I to the others. And this belongs to the action space of the agent I, which I denoted as calligraphic A, which, of course, each tie is a scalar between 0 and 1. So this action space is the hypercube 0, 1 in the n-1 dimensional space. It's n-1 because we don't consider self-loops in the network. And then we assume that every agent I is endowed with a payoff function Vi. So this payoff function depends on the topology of the network. We said that the network provides benefits to the actors. And the network in form of ties, so that's why we have a payoff function which depends on the action of the agent I and the action of all the other agents, A minus I, where we stack all the other vectors. And it's looking for the AI star, which is the solution of the maximization problem of this payoff function. So it's trying to maximize its own payoff. Of course, I need to be more precise on this payoff function. And here I'll take the contribution that I want to introduce in my payoff function one by one. So the first one, so it's composed by a different contribution, and the first one is the social influence on friends. So in this payoff function, I want to introduce, for example, the weighted in degree of the node I, measured as, of course, the sum of all the ties that starts from a node j and into node I. So this quantifies how much I is followed by the other agents j's. But I also want to go further than that, because we said in social networks we don't have perfect information, but we do have limited information up to a certain degree. So for example, we could argue that our social influence extends to the friends of our friends. So we have an indirect social influence. So that's why we consider paths of longer length, for example, paths of length 2 or paths of length 3, that, for example, starts from K to J and then from J to I, and from L to K, K to J, J to I. So these paths, they all end into node I. And they're discounted by a factor delta I, which models the fact that, of course, it's a parameter between 0 and 1, so that the influence that we have on direct neighbors is stronger than the influence that we have on indirect neighbors. The second contribution that I want to introduce in this payoff function is through this measure of the clustering coefficient. So this UI function that I defined basically counts how many of these triangular structures are surrounding node I. So here, as you can see, node I is friend with J and K, which are also mutual friends. So this situation, node I, receives social support from its friends. So that's why this measures the clustering coefficient of the node and the social support to the node. And a third contribution that I want to introduce is a cost. This is the cost for maintaining the relationships. So this cost function Ci is nothing else than the weighted out degree of the node I. So we said I is controlling is outgoing ties. So, and this estimates how much time does I spend on following the other agents' j's. And the last step I want to make is I want to introduce parameters in this payoff function, which I encoded into this theta I here, which is a set of alpha I, beta I, gamma I, delta I, set of parameters. And they allow me to basically give different importance to each of this term. For example, larger alpha I is associated with a stronger tendency towards social influence. A larger beta I is a stronger tendency towards social support. A larger gamma I means the ties are more costly. And you may wonder, why did I introduce the brokerage or the between centrality? And in fact, this effect here is encapsulated again in this second term here. So the reason is that beta I is the only parameter which is allowed to be negative. So when we have, for example, a negative beta I, someone that wants to maximize this payoff function is someone that wants to minimize the clustering coefficient. So minimizing the clustering coefficient means trying to minimizing the redundant connections of these types, the triangular structures. Minimizing redundant connections means we prefer connections to agents that are unconnected with each other, like this situation here. So between a centrality and clustering, or brokerage and social support, are basically two faces of the same thing. That's why they're both encapsulated into this UI function here. So far I defined a set of nodes N, payoff functions Vi, and the action space of the agents, calligraphic A. And these are the three elements that define a game. So now we started from the strategic network formation literature in economics, where the most common approach is to study the equilibrium of this game. So the equilibrium of a game is a set of strategies, which is of course in equilibrium. And in this case, strategies are nothing else than the network ties. So an equilibrium of the game is a network. So a G star, a network G star, can be a Nash equilibrium, or is a Nash equilibrium, if for all agents I, the payoff function of the agent I at any other action AI is never larger than the payoff function at the equilibrium strategy. So in other words, AI star, so the strategy, the equilibrium, is maximizing the payoff function given the strategies of all the other players, A minus I star. But of course, you may have noticed that we have a parametric payoff function that enters in the form of individual behavior theta I into the game. And at the end, that means depending on the individual behavior theta I definition, we may have different types of networks which are in equilibrium. So one first question that we may ask is the following. So imagine we fix the individual behavior theta I. Now we could ask which network G star is in equilibrium. So in fact, what we want to do is once we have theta I, we want to determine for all agent I, the strategy A star that solves this maximization problem. So this is in fact the common question considered in the strategic network formation literature, for which I would like to give a very short review. So in this, what you find is that there are several models that consider one single incentive at a time. For example, in their payoff function, they only consider agents striving for between a centrality or brokerage. And also they consider that all the agents have homogeneous behavior theta I. And what they found is that a stable network structure is, for example, of this type, a complete bipartite network. where if you look at it more carefully, each of the agents, for example, this one, is controlling the flow of information between any other two agents that are on the other side of the network. And in fact, each agent is striving for betweenness neutrality. If they focus on social support, if the agents focus on social support, then what they found is that the most stable or a stable network structure is the complete network. And for social influence, it's a star type network, for example, this one. So this brings me to the first part of our results. So here in our model, we have a parametric payoff function, which contains several different incentives at the same time. So we want to see how this compares with the results that were already known in the literature. So here we also assume that agents are homogeneous. So the theta I parameter is equal to theta for all the agents I, and that they are fully rational. And I'll come back to the rationality in the second part of the talk. So we consider 4 different stylized network motifs: empty, complete, balanced, bipartite, and star. And we use the variation inequality approach to derive necessary sufficient conditions for the stability, Nash equilibrium stability of these networks. So we can do this, and especially we can do this in a parametric way, in the sense that we can study the stability of all these network motifs in the parameter space. Here, beta over gamma and alpha over gamma. Just we can study this in this simplified parameter space. And what this result confirms is that, in fact, complete network is, for instance, associated with higher clustering, but at the same time, it's also associated with a tendency towards higher social influence. Conversely, bipartite and star networks, they do require a tendency towards betweenness centrality, right, which is the opposite of the clustering, and potentially also a tendency towards higher social influence. And the empty network, for example, is always an Nash equilibrium. But the interesting point here is that when I said we considered or we derived necessary and sufficient conditions, that means not only we started from a predefined payoff function and we analyze what is the stable network structure, but we also try to reverse engineering what are the parameters that underline a certain network structure. And I'll be more precise about this in the second part of the talk. So again, I want to repeat this. So before we were focusing on the question, given the individual behavior theta I that we can encode with some parameters, we want to understand which network is in equilibrium according to, for example, our Nash equilibrium conditions. But eventually, a more interesting question, which is often asked in sociology, in this stochastic actor-oriented models, is the following. Given G star, so a certain network structure that we observe, for which theta I is this G star in equilibrium? So typically in stochastic actor-oriented models, the approach is more statistical rather than a game theoretical one. And here we try to make it more rigorous in terms of parameters underlying a payoff function and in terms of rationality. So in particular, through our game theoretical inference, we want to find the individual behavior or individual preferences theta I such that the Nash equilibrium conditions, which are simply these, are satisfied. So the Nash equilibrium conditions that we observe from a social network structure are satisfied. And even we want to make one more step, which is we also want to introduce the possibility of having irrational behavior of the agents, which is also quite typical if we consider real-world social networks, which also can model the fact that our payoff function contains a number of possible sociological incentives, but of course there might be more than that. Or irrationality may arise from the fact that we also don't really fully observe the social network structure that is true in reality. So our game theoretical inference will in fact try to find the theta-eyed individual behavior that provides the most rational explanation to the social network structure that we see in place. So I talked about irrationality. That means, in fact, we need to allow for an error function, so possible deviations from the Nash equilibrium. So that's why we define an error function which depends on an action AI and on the unknown individual behavior theta I, and it's based on the difference between the payoff function at another strategy AI and the strategy that we observe AI star. So now positive contribution of these error functions, they correspond to violations of the Nash equilibrium conditions, because it means that there is a strategy AI that would give a higher payoff with respect to AI star, assuming that the individual behavior is theta I. So if we only consider the positive part of this error function, and we do integrate into the all action space of the agent, so calligraphic A, that means we compute the L2 norm in the action space of this positive error function. We basically measure a distance of an individual behavior theta I with respect to the Nash equilibrium conditions. And obviously, what we want to do is we want to find the vector of preferences, theta I star, that is the minimizer of this distance function. So it's the minimizer of the violations of the Nash equilibrium conditions. So naturally, the first question we should start asking is whether this problem, this minimum Nash equilibrium distance problem, is well posed. And according to the theorem, the square of the distance function, whose minimizers are, of course, the same as the minimizer of the distance function itself, is continuously differentiable. And also, we can prove that it's convex. So that means there is a minimizer for this square of the distance function, which might not be unique, but there exists a minimizer for sure. And actually, I would like to go a little bit more into technicalities of the solution of this inverse optimization problem. So first of all, let us assume that the minimum is 0. That means there exist solutions that fully satisfy the Nash equilibrium conditions. Then we have a theorem that says that, first of all, the solution is not necessarily unique, but it's a polyhedron. So I call this set of solutions that fully satisfy the Nash equilibrium conditions capital theta I0. And I would like to briefly sketch the proof of this result. So first note that the minimum, we assume that this minimum is 0. That means that given the definition of our distance function, if the minimum of this is 0, it means for all the theta I that are solutions, that then the error function cannot be strictly positive, but actually has to be smaller or equal than 0. So that when we only take the positive contribution, then the distance function is 0. But this set theta I0, we can equivalently rewrite it as the set of all the theta, such that the error function is not positive for the maximum of the strategies in the action space. So the maximum of this error function for AI in the action space, calligraphic A, has to be smaller or equal than 0. And then I will focus on this error function. So this error function is a linear combination of the parameters, and it's also a combination of linear and mixed quadratic terms. I cannot show this in the interest of time, but it's a linear and mixed quadratic combination in the terms of AI. But what I want to stress is that there are no pure quadratic terms of the type Aj squared. That means if you look at the Hessian matrix of this error function, since there are no pure quadratic terms, then we have 0 on the diagonal. That means the trace of this Hessian matrix is 0, which also means that the sum of the eigenvalues of the Hessian matrix has to be 0. So if we're looking for a maximum of this error function, well, we know that any critical point of this error function in the compact sets calligraphic A can only be a saddle point, cannot be a strict maximum. That means there cannot be interior points that are strict maximum. That also means that if there exists a maximum, it must be attained on the boundary of the action space. And the boundary of the action space is composed by 2 times n minus 1 sides, and each side is now the compact set, so the hypercube 0, 1 in the n minus 2 dimensional space. And we can proceed by induction because when we restrict the error function to the boundary, then we have the same property. So at the end, what we only want is that this the theta I that are in this theta I0 set of solutions that never violate the Nash equilibrium conditions are such that the error function is always a non-positive for all the strategies which are in the corner points of our action space. So generally, because here we are integrating this error function over the whole action space, we wanted, or initially we wanted to be negative in all the points everywhere. Now it's sufficient to check only at the corner points. But that means that we have an algorithm to find this set of solutions that fully satisfy the Nash equilibrium conditions. In fact, this error function here, at each corner, this error function or this inequality defines a half space for the parameter theta I. So if we want this to be more or equal than 0 at one single AI, one corner, that means we define a half space. And we need to check for all the possible corner points of our action space. So at the end, what we have is that theta I0 is the intersection of finitely many half spaces. And in fact, that's the end of the theorem, because if a set of exact solution to the Nash equilibrium condition exists, it can be found as the intersection of finitely many half spaces. But of course, so far we said, okay, we assume that there exists at least one solution, which actually we see it's a polyhedron, that fully satisfy the Nash equilibrium condition. But what if this polyhedron is actually empty? That means there is not an individual behavior, so a theta I set of parameters that rationally explain the actions of the players. So in this case, what we could do is we know the problem is well posed. So then we know the square of the distance function is convex. So we could instead use first order optimality condition, right? To find a solution of our problem. But the issue here is that to solve first order optimality condition, this involves a max operator that comes from the fact that we only consider the positive part of the error function within such an n-1 dimensional integral, which is the action space. So long story short, even if you try to remove the max operator, and so you integrate over a reduced calligraphic A plus action space, which is the set of all actions that violate the Nash equilibrium conditions. This cannot be solved in closed form for the individual preferences because the integral region depends on our unknown theta I. So what we could do in this case is we could search for an approximate solution. So basically we consider discretization of our action space with a set of possible actions, samples, and we consider the errors, so the violations of the Nash equilibrium conditions at this given samples. We approximate the distance function. So before it was the L2 norm of the error function. Now here we consider the 2 norm of this error vector. And we solve the discrete minimum Nash equilibrium distance problem, where we want to find theta I hat that in this case are the minimizers of our discrete distance function. So the good news is that this the discrete minimum Nash equilibrium distance problem has the same properties of the original one, the continuous one. So there exists a solution. The problem is that, again, it cannot be found in closed form. However, through a projective gradient method, it's possible to find a solution. And I'm skipping some of the details of how to find the solution, but what I want to stress is that we may want to know how good is the approximate solution. So the approximate solution here is the fixed point of this equation here. It's this theta I hat. And it closely resembles, in fact, the solution of an ordinary least square regression problem. And in fact, we can make a similarity between our discrete minimum Nash equilibrium distance problem and this regression problem. So I want to highlight just the 2 main differences. So the first one is that, in fact, in regression, it's possible to find a theta hat in closed form, which is something that it's not possible in our case. And the second one is that in regression, one typically assumes that the errors are normally distributed with 0 mean and sigma square variance, for example. In our case, the residuals are all non-negative. That means we need to assume that they have an exponential distribution whose parameter we can estimate from the data, and from this we can define bias and the confidence intervals on our estimate theta I hat. So basically this is just to say that not only we find a solution, but we also try to understand how good is this solution given the fact that we are solving the discrete minimum Nash equilibrium distance problem. So this brings me to the second part of our results. So we, after deriving this theoretical methods, we applied it to a couple of real-world case studies. The first one regards the set of network ties between members of an Australian bank. So the network is plotted here on the left and displays all the elements of the network with darker color associated to nodes which have a high ranking position, from the branch manager to deputy manager, service advisors, and tellers. So just by inspecting the network, it's maybe one could understand or could realize that there are a couple of interesting observations. For example, the tellers are mostly on the periphery of the network, and there is a tendency towards a star type network embedded in the whole network, which is centered into, for example, the service advisor tool or the branch manager. But it's pretty hard to understand what type of behavior in terms of between a centrality or social influence or social support do these agents have. So in order to do so, we run our behavior estimation method. So from the data that we observe, we try to estimate the parameters associated to each of the agents. And interestingly, what we found is that most of the agents that have high ranking positions, for example, branch or deputy managers, they have a tendency towards between a centrality. So they try to control the flow of information between the other members. So they really have a competitive behavior in the network. Conversely, tellers have a higher tendency towards maintaining form of social support, so higher clustering. And some other observations regards the social influence. But for this, for example, we can see that at any hierarchy level, there can be agents that strive for higher social influence, despite the fact that most of the tellers have a lower tendency towards increasing their own social influence. So, and then I would like to present our second case study, which regards the network of relationships between, it's a famous data set that concerns the network of relationships between 15 families in Florence during the 15th century. So these were all very powerful families, and they were connected with each other through marriage and business ties, which are represented here in the network with the different colors. So this has been a data set that has been studied historically because basically what was very interesting about that is that the Medici was the only family that was able to rise in power at that time. And also what they found through historical studies is that the Medici really strategically decided with whom they wanted to make marriage relationships or business relationships. In fact, for example, what Paget and Ansel found is that the Medici were trying to basically segregate the people with whom they were doing business or marriage ties. In this way, they were able to prevent the dissent that could rise between their neighbors. And when we try to estimate their behavior with our method, we in fact find that the Medici, so when considering marriage ties or business ties separated, what we find is that they really try to maintain a behavior with a tendency towards between a centrality. So controlling the information in order to prevent a possible descent. But the interesting part is that when we consider that two types of networks superimpose one with each other, so the combination of the two networks, and we analyze this combined network, then, and we try again to estimate the behavior of this family, it appears that they were able to achieve a large social support. So despite the fact that they were able to control the information when considering their marriage ties or business ties, then at the end, combining all together, they were probably able to achieve the social support from all their neighbors, and maybe that was the key that could explain their success at that time. So before concluding, I would like to make a last connection towards the complex networks community, which proposes, as I said in the introduction, a number of network formation models based on statistical rules. So the most famous one is the so-called preferential attachment. So this preferential attachment is associated with the famous reach-get-reacher phenomenon and the scale-free network effect. So the idea behind that is that the likelihood that a new node is connected by other nodes is proportional to the degree of this node. So for example, the higher the degree of this node, the higher the likelihood that a new node will connect to this guy. So originally the preferential attachment model was proposed for undirected networks. So here we studied a directed version of the preferential attachment model, where basically we start with a couple of seed nodes, which are mutually connected. And then the nodes are introduced sequentially. So each newborn node receives two incoming links from existing nodes, which are randomly selected proportionate to the out degree. And it creates two outgoing ties to existing nodes, which are randomly selected proportionate to the in degree. So in this way, we have this reach-get-reacher phenomenon both for the in degree and the out degree of the nodes. Whereas in the regional preferential attachment model, this works for general, for the degree of the node, because in degree and out degree are simply the same. So we run 50 different types of simulations of this network formation model. And what we try to do is we try to analyze the behavior of the newborn node inserted at time step 3, 4, 5, 10, 200. So, and what we realize is that when the network is still small, the connections that this newborn node chooses according to the preferential attachment rule can be associated with a tendency towards social support and the social influence. But the more the network grows, the higher the tendency towards between a centrality, so they try to connect to disconnected others, and to lower social influence. So this example is just demonstration that we can apply our method to more famous random networks model that are based on statistical rules, statistical mechanisms, but they are lacking their sociological explanations. And in this way, we can try to give a sociological interpretations behind the statistical rules. And before concluding, briefly present also this a second applications to this random network model, which is the small word network. So small word network is a model that started with, say, from the definition of, say, a lattice. So we have a lattice of nodes, and what Watson Strogatz proposed in this original model is that rewiring some of these edges in the network will allow to shrink the diameter of the network. For example, you can start from this lattice here, and rewiring some of the nodes, basically the nodes are more closely connected. So here the diameter is 2 because each node, sorry, the maximum connection between two nodes is at distance 2. Here it's, I believe it's 1. So basically this model was proposed because of the famous experiments on the 6 degrees of separation, where, you know, it has been found that each 2 agents in the world possibly are connected by at most a path of length 6. So here we started several different types of small word network models. So from a pure lattice to, say, complete network. So pure lattice here is when a node is connected to the first one on the left and the first one on the right. But we can increase the number of neighbors so that the node is connected to 2 guys to the left and 2 guys to the right. So here we consider networks of 11 agents. So at the end, when each node is connected to 5 to the left and 5 to the right, we have a complete network. And again, also here, we try to apply our behavior summation method in order to understand what is the behavior that can explain the networks emerging from this random networks model. So we started it in, as a function of number of neighbors, so how much the network is sparse or dense, and as a function of the rewiring probability P. So from a regular lattice to a random, fully random reconnections of each tie. So what we find is that when the network is fully dense, so it's a complete network, agents are striving for higher social support and higher social influence. That confirms our own theoretical results on the complete network, in fact. Conversely, when the network is really sparse, then each agent here is controlling the flow of information between its left and right sides. So basically, each agent is striving for between centrality. And here we have a shift from the social support, the clustering, towards the brokerage. And then the more we increase the rewiring probability, the more we destroy the symmetry of these connections, which reflects in reducing the social influence, the tendency towards the social influence of the nodes. So, but this brings me to the conclusions of the talk. So I want just to summarize, briefly summarize what was this talk about. So we started from the strategic net information literature, and we propose a model which is try to convince it with that is sociologically well-founded. It's mathematically tractable and also statistically robust. And it's capable to basically reverse engineering the human behavior in terms of individual incentives or parameters from easily accessible data on the network structure. We also provided evidence that the results are consistent with empirical, historical, and sociological observations. And finally, we also proved that the method can offer socio-strategic interpretations of random network models. And as future directions, the model can be adapted to further specifications of the payoff function. So far, we consider a number of sociological incentives, but especially the method where we do this game theoretical inference as can be generalized to any other type of different payoff function, and potentially even any other type of game, because it's only an inverse optimization problem that we're trying to solve. And also, we think that we could incorporate prior knowledge on the action space. For example, imagine that agents can only decide a certain number of ties that they can choose at a given time. And that can reduce the computational burden, because right now it scales exponentially with the number of agents. And the last one is that we could also include attributes to the actors that so far have not been considered. And with this, I would like to thank you for the attention, and I'm happy to take questions.
Thank you very much, Nicolò. Very interesting talk. Does anybody have a question? Okay, I have one actually. So you have shown us some of the applications you have been looking at, but do you have an application in mind where this could really be applied in the future? Like out of the applications you listed, is there a specific applications in the real world that you think this is really good for?
So I think generally trying to understand, so especially the reverse problem of understanding the individual behavior in social networks and how they are formed, I think it's potentially very interesting in terms of how do we design the social networks, especially with the explosions of nowadays social networks. You really want to know what are the agents trying to do on the social networks. So I don't have a specific application in mind that's true. I mean, basically, I think the method itself shows that, say, we need to change focus, especially at the beginning. I try to highlight this quite clearly. The original problem was, imagine we know this individual behavior, then we would like to understand whether a stable social network structure can be, for example, a complete network, which could be applied in politics as, for example, you want to know whether you have a democracy or an autocracy or something like that. But this turns out to be not really applicable, because real-world social networks are way more complex than this stylized network motifs. So in the examples that I show, you cannot really distinguish any complete or bipartite networks. You cannot distinguish that, just because the individual behavior of each of the agents is really different. So starting from assuming that we know this individual behavior, it's probably the wrong assumption. So solving the inverse problem is potentially the most interesting one. And especially recently, I've seen that there are a number of studies that are also trying to, doing some online learning of this individual behavior. So especially, so here it's a theoretical analysis, and we try to say find our behavioral estimation in the most rigorous way with confidence intervals and so on and so forth. But assuming that also we observe a snapshot of a social network which is somehow stable. But the reality is that the social network structures are changing very fast. And what you want to do is you want to do some online learning through data which are, again, very easily accessible. And with this data, trying to infer what is the behavior of each of the agents online. I think this is a quite promising direction in the coming future.
Thank you very much. Very exhaustive answer and very interesting work. Is there other questions? All right. I think you by now you know how to reach out to Nicolò if you might have questions in the future. And with this, I would thank you again, Nicolò, and close the Autonomy Talk and see you next week.